So, first of all, because not everyone knows where Rostock is, I brought you a recent map that's from about 1400. What you can see is that this is the Baltic Sea, this is the North Sea, this is what then later on became Germany, this is a bit of Poland, Lithuania, and the rest of it. Rostock is one of the, or used to be one of the major cities of the Hanseatic League, so the precursor of NATO, if you wish. And so Rostock's over here. Berlin used to be a very poxy little village in 1400, it's around here, completely unimportant, still is. So what I'm going to talk about is about lateral Casimir-Polder forces, where they might arise in various different systems. I'll then talk about the directional spontaneous emission near tapered optical fibers, so I'll introduce that topic of tapered optical fibers, and I'll give you an explanation where this particular type of natural forces might actually arise from, and the buzzword there, which I didn't invent, is spin-orbit coupling flight, and I'll come to some conclusions in the end. So, I probably don't have to introduce what Casimir-Polder forces are, just do it anyway. And it's one particular type of dispersion interactions which usually we consider between a neutral polarized particle, atom, molecule, whatever you like, described by some dielectric polarizability, and some macroscopic body, just here sketched by a block of material with some permittivity epsilon. And of course, we all know it's mediated by either ground state or thermal, whatever fluctuations of the electromagnetic field. And it's actually typically attractive, or it's always attractive in thermal equilibrium. So when the atom here, or molecule, is in thermal equilibrium with its environment, including the macroscopic body, but it can be made repulsive in some special circumstances, for example, thermal non-equilibrium situations when you place or prepare the atom in an energy eigenstate, which is, of course, sort of a prime example for a thermal non-equilibrium situation. And then, because, for example, if you have a sort of plain slab surface, because of translation invariance, the force has to be perpendicular to that surface. Yeah. And of course, the question that may arise is, do these Casimir-Polder forces exist and are also parallel to such an interface? And we've just seen one example by Francesco, and that's friction force of atoms in motion. But there are also these lateral forces that can arise, and I'll talk about those during the rest of the talk. Now, this is of course a fairly simplified picture of how these Casimir-Polder forces arise in one simple atom, in one very simple geometry. In typical experiments, it looks vastly different. So this is, in typical situations in which Casimir-Polder forces arise, this is a sketch from an experiment performed at, the other university in Vienna. This is a molecular interferometry experiment with large molecules, in this case a diene molecule of cyanide, which travels through a grating which has a particularly interesting or complicated structure, and what you find is these molecules interfering at the end, and you might actually try to retrieve some information about the interaction of those molecules with these grating bars, the Casimir-Polder interactions, from these interference pattern. And there's even one person sitting over here who's giving a poster on precisely that, on how to reconstruct polarizabilities or Casimir-Polder potentials from these interference patterns. There's a poster whenever the poster session is. So, coming to this natural Casimir-Polder forces, it's been of course known for quite some time, and I've listed here already 2 papers by Diego and Paulo Mainetto, where these lateral Casimir-Polder forces might arise, and typically it's considered to be a geometric effect, where the surface, which I depicted in the previous picture as just a plain slab, translation invariant, might actually exhibit surface corrugations, and in these cases you might argue that, of course, this particle here might have a perpendicular force component to that piece of material, but not to this, and you get an effective lateral force, somewhere across this corrugated interface. This is one example of where these lateral forces might arise. A second is in fact, translationally invariant situations with a very under very specific circumstances. And this is the experimental setup that we have in mind. It consists of, well, the central object here is a so-called tapered optical fiber. This is nothing else than a single-mode optical fiber with the typical core diameter here of about 1 micron, so it carries a single mode of, in this case, 852 nanometer light. Reason for these 852 nanometers will become apparent in just a couple of slides. Which is these fibers being pulled over a hydrogen flame to a diameter of on the order of about 500 nanometers. Which means that as an optical fiber, it doesn't work. So it wouldn't be able to carry this optical mode that it would be able to carry here in this single mode picture here. But what it does is, tapered means that this length scale over which the diameter of the fiber decreases is very large compared to the optical wavelengths. So this is on the order of a couple of millimeters of length. And what happens is that the optical mode that you launch into this core here will actually slowly, adiabatically, leak out of the optical fiber and be carried as an evanescent wave propagating along the fiber. Right? So most of the intensity will actually be carried not inside this still existing piece of glass, but outside it. Right? And of course what we will eventually want to look at is we will look at atoms, individual atoms being trapped, for example magnetically trapped, somewhere sort of below or above that fiber there. Okay, so the first thing that one has to notice is a very interesting effect, of course, on which these lateral forces are based, and that is the fact that if you start launching a linearly polarized light into this single mode fiber, the micrometer sized fiber, for example either horizontally polarized or vertically polarized, upon hitting that tapered region, where the wave in fact turns evanescent, if you look at the polarization state of light, at any instance along this tapered region, it won't be transversely polarized. In fact, that's what I really mean. It's not transversely polarized any longer. So what is plotted here is just a normalized field intensity in two different polarization directions. So basically, the fiber goes into the board here. And what you see here on the top line here is the intensity components of the electric field decomposed into the various polarization components, sigma plus polarized, circular polarized light, with light propagating into the negative Z direction, or respectively sigma minus polarized light with the light propagating positive Z direction. Here's the opposite polarization or the opposite propagation direction, and here's the pi, that is the linear polarized light, where you see there's actually no linearized component outside the fiber. It's always circularly polarized. And in fact, the circular polarization takes one component from the original linear transverse polarization plus a piece of longitudinal polarization in the direction of the fiber. And that polarization, circular polarization, is dependent on the propagation direction. This is what is noticed here. And the left side here will be sigma plus polarized if the propagation direction is in minus Z, and it's sigma minus polarized if the propagation is in sigma plus Z. Which is an interesting effect, so it couples the polarization degree of freedom outside that fiber to the propagation direction. And this is what people sometimes call spin orbit coupling of light. Again, it's not a word invented by me. So what we have in mind is a piece of nanofiber. This is now just the 500 nanometer bit with an atom being trapped relatively close by. This is possible down to distances on the order of 200, 250, 50 nanometers. And what you would see is that if an atom would be sort of radiating, spontaneously radiating, it will couple preferentially in one of the modes which would go along the nanofiber only in one particular direction. So So what would you need in order to do that? Of course, you have this fiber with this particularly interesting property that the polarization on one side of the fiber is dependent on the propagation of light. But then, of course, you need an emitter which actually produces that precise polarization. So you need to produce an either sigma plus or sigma minus polarized photon. Well, that's easy. Well, I said you trap an atom close by, and here is, if you look at the structure, the electronic structure of cesium atom, you start from the ground state, the 6s1/2, and you choose that particular electronic transition from a 6p3/2 state down to the 6s1/2, and that has a wavelength of 852 nanometers. So that's what I was saying before. But you also look at the hyperfine structure of those levels. You notice that this 6s1/2 state has an f equals 4, so it has different hyperfine sublevels from -4 to +4. This state up here has hyperfine levels from -5 to +5. And if you prepare the atom initially in an excited state, electronically excited state 6p3/2, and in that hyperfine level, the only way it can decay is down to that state, emitting a sigma plus photon. So that's a chiral emitter, if you wish. And of course, you could place it over here, and it would radiate a sigma minus light. And that's the only way it can emit spontaneously a photon, that would sort of couple directionally into one particular direction along the fiber. So this is a video purporting to show this. If it would work, yes. So here's just a short video showing that if there's an emitter radiating circularly polarized light, it will actually preferentially emit in one particular direction. So, people have shown, the group with the experimentalist around Arno Rauschenbeutel have actually shown that they can get an asymmetric coupling to one side of the fiber to the other side of the fiber of up to 40 to 1. That's really a very nice directional emitter. So, and we quantified that, how that would look like roughly if you placed an atom sort of somewhere, 200 or 250 nanometers away from that fiber surface, which is, as I said, about 500 nanometers in diameter. And you can look at the contributing modes in which the atom will decay. There are radiating modes. So for example, this solid line here, these are the radiation modes to the plus Z direction. These are the ones to the minus Z direction, and the guided modes respectively down here. You see that's already in a symmetry which we can quantify by some directionality parameter, which is the sum of partial decay rates weighted by the wave vector projection onto the fiber axis. And here, for this particular fiber that we've been looking at, you see this directional parameter increasing as you go into the near field, and in the far field actually being oscillatory as you go away from the fiber. So that's already the far field regime. So, of course, everything depends on material parameters, and this is just to show you that we can actually calculate things. So if you look at the total spontaneous decay rate, of course, we already know this is proportional to the local density of states encoded in the imaginary part of the Green's function. Dipole moment of that particular cesium transition is this value, and we compute this directionality parameter as well. It's the imaginary part of this off-diagonal component of this Green tensor. This is just divided by the sum of the diagonal components, giving you the total weight of the entire spontaneous decay rate. Okay, so we now know that an atom placed in a particular quantum state will emit circularly polarized light, and therefore will emit light in a particular direction along the fiber. And of course, the next question you might ask is, well, if it emits a photon preferentially in one particular direction, there's a recoil associated with it, that gives you a force, doesn't it? Right? So, but that's of course not the first system in which these directionalities have been found, or have been proposed. In fact, I believe the first instance of a geometry-induced chiral interaction, as it's called, has been found also experimentally in this Fusser letter from 2013 from the group around Maurice Skolnick and Mark Fox at the University of Sheffield, where they placed quantum dots in a sort of in a fiber, in a waveguide cross, and depending on where exactly they place this quantum dot, they can actually see an emission either to the bottom and the right, or to the top and the left of those waveguides, including these particular polarizations. So this is not the first example, what we have proposed. I think this is the first example. So, and now I come to the origin of this chiral coupling, and I said this has to do with what, when I say people, I mean particular Konstantin Bloch, what he calls the spin-orbit coupling of light. So, which is nothing else than the coupling of the polarization and the orbital angular momentum of light. And the necessary requirement for that spin-orbit coupling is either a tight focus of a laser beam or a near field. So that is the coupling to some evanescent modes. So here's an example of a calculation from these two papers from Konstantin Bloch and his co-workers, showing that even at a flat surface where you have some evanescent field modes, if you shine a laser light from behind into the sapphire crystal here, which gets totally reflected, so you get an evanescent wave coming up here, you will actually see a directional, a chiral component of the force on, for example, a going nanoparticle. And I believe the simplest reason for why this chiral coupling comes about is because you have, a strong directional dependence, or actually a strong geometric dependence of the wave factor. Of the field component in a particular direction. So if you start from your relation that the divergence of the electric field must be equal to 0, then if you look at, for example, an evanescent wave, then you find that, of course, kx and ky, for example, are sort of real numbers, and the wave factor component in z direction is complex, and an out-of-phase relation between these transverse and longitudinal wave factor components, and that indeed converts the linear into the circular polarization of the light field in the near field. So, what about the natural force? So this is just a few formulas. I go through them. So what we look at is, of course, the ensemble average Lorentz force. So the gradient of the expectation value of E dot E, which, as usual, we decompose into two different components, what we call the non-resonant and the resonant force components. The non-resonant one is what you calculate in thermal equilibrium, so the usual Lifshitz theory, whereas these resonant components come if you, for example, have the atom placed in the excited state, which is precisely the situation here. Turns out that this non-resonant force component is proportional to the symmetrized green tensor, the gradient of the symmetrized green tensor, and it turns out, as you would expect or hope, that this contribution is actually always 0 because of translational invariance along the fiber, otherwise to relate various thermodynamic principles. But the resonant component is, in fact, given by this expression here, and it's just the derivative with respect to the fiber direction of this imaginary part. And that is indeed associated with the recoil of the atom during the optical transition from the excited to the ground state. So, what I've noticed here, that typically in normal resonant forces, these Casimir-Polder forces, the resonant components, they go with the real part of the Green's function here. In this case, they go with the imaginary part, and that's precisely this out-of-phase dipole oscillations that I'm talking about. So, how does it approximately look like? This is our calculations for this lateral force on a single circular emitter, so a single cesium atom in a maximal MF state, or I should have said modulus MF state. So this is roughly the near field. What you see over here is the force along the fiber in zeptonewton. And you would think, well, this is not a lot, but it's huge, absolutely, because you can actually compute the mean natural velocity kick on one single atom per emitted photon. That's a much more sensible value, and you see that this velocity kick gets up to almost a millimeter per second velocity kick per emitted photon, and that's something that we believe can be measured at some point, and this is why we actually do the calculation. So, of course, I've already mentioned that there are alternative realizations of the same scheme. You don't need a fiber. You can actually do that near a slab which also carries evanescent waves in terms of surface plasmons, and then you get some time average lateral force, which these people have just shown last year in Nature Communications. So, and I believe time's up for me now, almost. So I come to the conclusions. There's one misprint, I'm sorry. So we have a spin-orbit coupling of light in evanescent near fields, which, as I've showed you, actually leads to a coupling, and it's a rather efficient coupling of the polarization and the propagation direction of light. When I say rather efficient, it's been shown to values of, or ratios of 40:1 coupling. You get strongly directional spontaneous emissions of atoms near nanofibers. And of course, this emission direction, as I showed, can be controlled by the choice of quantum state, in which quantum state you initially prepare your atom in. And then, of course, you might ask the question, well, hang on a moment, if I can prepare or control the emission direction by preparing the atom in one particular quantum state, why not use a superposition of two? Right? And then you can start talking about path entanglement of atoms being kicked in one or the other direction. So you can actually look at the generation of entanglement. But more to the point, it's actually interesting for optically driven self-organization of trapped atoms, because you can excite an entire ensemble of atoms that will actually be kicked and sort of orient themselves in particular directions that might actually sort of fit into regular structures. And that's something that our experimental colleagues work on at the moment. So, and I believe that's it, and I thank you for your attention.
Thank you very much for this very clear presentation.
So the force with the imaginary part of this thing. So it's a random force, or it's a conservative force, or it's a random force. Is it? The atom has to be excited.
Yeah, the atom has to be excited, and what it does, it releases its excitation and gets a kick. That's all.
All right. So
it's a single kick. If you want to sort of accelerate it, for example, even more than just 1 millimeter per second squared, whatever, you have to re-excite it again. So it has to reabsorb another photon. But the interesting bit is, if you look at the geometry, the excitation is in a different direction than the atomic emission. Here we go. So the excitation is basically along the y direction here, so it's perpendicular to the fiber, whereas the force and of course the directional emission is along this direction.
So basically, you get if the fiber, if you had no confinement, basically, so you had no. The field was transverse. Let's say the field was transverse. Okay. So then you will also have these kicks, but the average force would be 0.
Yes.
It's a random walk, but the average will be 0.
Yes, absolutely.
Here, because you have this directionality, if you excite only the sigma plus transition,
with the 40:1 chance you go in one direction rather than the other.
So again, it's a random force, but it has a mean. It's a random walk with an average.
That's what I meant in the end by the ensemble average Lorentz force. Absolutely.
The radiation pressure force.
Sorry?
It's not ridiculous.
The radiation pressure force invisible.
Yeah.
So I have a question. So basically, if I understood correctly, here there is a breaking of the symmetry, the reflection property about the plane and Z equals 0, right? So that's why we observe this lateral force in this dipole.
Well, this is interesting, because you don't see from this sketch here that there's any symmetry breaking along the Z direction. You don't see that. If you just look at the picture, where's the symmetry breaking? There's none. It's really only the fact that the evanescent modes that are basically traveling on this fiber here, coupled to the direction of the propagation along that fiber. So it's not a geometric symmetry breaking. I wouldn't call it like that. It's a propagation symmetry breaking.
Propagation. And what's happened to chiral molecules? Because I was interested about that. So basically, here there is this strange feature about
what would happen to
lateral force.
Well, of course, I don't No, what would happen? Because you don't need, well, the only thing you need is you need a selective, sort of a polarization selective emitter. That's all you need. That's what I call chiral here in this context.
Okay.
Only the a polarization selective emitter. So this is you know, a cesium atom is already good enough as a polarization selective emitter because you can prepare a particular quantum state that emits only circularly polarized light with respect to, of course, with respect to that quantization axis there.
Would it be possible to have a surrounded gas outside with a specific refractive index? Then it might be possible in principle to measure the Minkowski transfer momentum in analogy to what Catalyst did in 2004.
So you would like to have not just one atom but an entire gas?
Yeah, a gas is the atom or the particle in a gas consisting of the particles making up a medium with a definite refractive index, because the kick will be dependent on the value of that surrounding.
Oh, so we'd like to immerse this particle
Right.
in a gas
Right.
of otherwise, well, of other atoms that would not be subject to that lateral force, and you would see how it drags through that particular gas. I think theoretically this is a good question. I think I try to sort of answer for on behalf of my experimental colleagues. The trap of these atoms, rather close to the surface, is fairly low. So these experiments have to be done in ultra high vacuum usually. So you wouldn't like to have many atoms around that could scatter off this one here. And that's of course precisely what you want in order to have a medium that gives you a refractive index. So theoretically, yes. I think experimentally, no.
In the setup you described, the atom has to be put in the right state, so with right hand.
Yes.
But imagine you have hollow optical fiber. So optical fiber with a hole
Yes.
parallel to it, and the atom will be inside. Then it will be independent of the orientation of the atom.
Yeah, because if your atom is inside in the hollow core fiber, then of course if it's on the axis, there is no.
And still there will be
Symmetry.
directional emission.
Well, yes. If you're able to define for that particular atom, if you're able to define a quantization axis, which has to be perpendicular to the fiber. So you have to shine through the fiber to excite your atom, keep it there. Because otherwise, with respect to what axis do you define sigma plus or sigma minus? Right? So you have to define a particular axis. In this trapping situation, this is easy. It's done by the trapping laser beam or by some excitation laser beam. That gives you the direction which defines sigma plus or sigma minus. Inside the fiber, to think about it, whether this works. Right?
This makes me think of an old paper of me, where I studied in an evanescent wave a combination of the two principal polarizations called TE and TM.
Yeah.
And if you choose the right amplitude ratio, you can create a circular polarization with respect to an axis that is tilted. Yeah, it's in the plane somewhere of this totally reflected laser beam.
Yeah,
but it's tilted.
if you go along the
And then we found that the radiation pressure force was tilted too. Yeah, it's not along the direction of propagation of this evanescent wave, but off this plane.
And the reason is presumably because it's still a propagating field. So if you look along the fiber, the polarization actually sort of rotates like that in a kind of sort of spiral fashion. So presumably the plane of actual polarization is always tilted towards that. That might be the case. Yes, absolutely.
Well, you can get fibers that's just that have only propagates a certain circular polarization, can't you? So could you have that and then use one of those with essentially for your chirality, and then have a sort of a homogeneous radiation of what happens?
The first thing what you would like to have is you would like to have the coupling of your atom or your emitter to the light field in or outside the fiber.
Yeah, so
Right?
it has
So,
to make
so
one
it has,
use
it
and
has to
then
be, has to be
pull
one
it
of those nanofibers anyway, because
Yeah.
you have to have sufficient amount of light being traveling outside as an evanescent guided mode. And I'm not sure whether you were still then able to have fibers that only support one polarization.
Yeah, I don't know if anyone's tried pulling a PM fiber or a chiral.
I'm not aware of anyone having tried that. I think it's just standard fibers to pull them. I guess this is a dirty mechanism of actually just pulling it over the flame. I don't think it will maintain any polarization.
No, but if you could sort of construct it.
I'm not aware of this. So.
Okay, I would say thanks again.